So we've spent some time talking about solutions, solution formation, different concentrations we can use to describe solutions, and now let's get into our colligative properties. Specifically in this module, I'm going to discuss vapor pressure. We did talk about vapor pressure previously, but now we want to go ahead and examine it a little further and see what's going to affect our vapor pressure. We also should be able to use Raoult's law to determine the effect that a non-volatile solute has on a vapor pressure of a solvent and determine the vapor pressure of a solution that contains two volatile components. Remember, volatility is when something easily escapes from the solution. It has weaker IMFs, which allows it to reach the vapor phase, higher vapor pressure. More particles are able to escape into the gas phase from the solution. So is only one part of it volatile, only one thing in the solution escaping, or are multiple things being able to escape? And we should also understand how solute-solvent interactions can result in a positive or negative deviation from Raoult's law. We are going to consider 4 different colligative properties. Again, in this module, I'm specifically going to focus on vapor pressure, but colligative properties are properties of solution that depends on the number of solute particles, not their identity. The identity of the particle themselves is not what's determining the property. It's the number of particles that are determining the property of the solution. It's kind of like when I teach a class. If I'm teaching a class of 20 kids, I get to know my students a lot better than if I'm teaching a class of 200. In the 200 class, some students I just don't get to know as well because class is just so large. It's a number-dependent system. But I'm still teaching the same content no matter which class I'm teaching. So colligative property based on numbers. We will consider 4 different colligative properties. We're going to talk about vapor pressure, specifically vapor pressure lowering, boiling point, specifically boiling point elevation, freezing point, specifically freezing point depression, and osmotic pressure. But again, this module I'm going to focus on vapor pressure and vapor pressure lowering. So as a slight review from previous chapter when we talked about intermolecular forces, I do need you to understand what is vapor pressure. So we're going to cover the same thought experiment we've covered before. Let's say we have a chamber that's completely evacuated. And in this chamber, I put a single block of ice. I then slowly warm this to room temperature. And what's going to happen? Well, naturally, we expect that ice to melt, right? Except that it doesn't just melt. Some of those water molecules are actually going to escape into the vapor phase. And we expect that. We know that if we leave a glass of water out on the countertop, eventually over time, all of that water, if it's an open system, that water will evaporate away. But it hasn't reached the boiling point. How did the water enter the gas phase if it hasn't reached the boiling point? Water doesn't boil until 100 degrees C or 212 Fahrenheit, but room temperature is about 25 degrees C or about, 70, 75 degrees Fahrenheit. How is that water escaping into the vapor phase? It's because water has a vapor pressure. And so what we've created in this chamber is an equilibrium between water in the liquid phase and water in the gas phase. Water in the gas phase we call water vapor. Vapor pressure is the pressure pushing, so these vapor particles are pushing on this liquid. It's the pressure pushing on that liquid from the particles in the vapor phase. They're a gas, they're in the vapor phase, therefore they exhibit a pressure. We talked about it in gas laws, PV equals nRT, we can actually calculate the pressure of that system, but that vapor does exhibit a pressure on the system. The vapor pressure, the pressure due to the vapor above the system. And again, you will talk about equilibrium very, very soon. It's another chapter we're going to spend weeks upon, or it feels like weeks. We're going to do lots of different systems with equilibrium. We'll spend a short time on basic equilibrium and then delve more into acid, base, etc. But what's happening here is these particles are constantly changing phase. Some of these gas molecules are condensing down to form liquid, while some of these liquid molecules are escaping to form more gas. The thing is, it's happening at the exact same rate in the forward and reverse direction, meaning liquid is escaping to the gas phase at the exact same rate that gas is condensing down to the liquid phase. So from a bird's eye view, we don't notice the change at all. It seems constant, but at the molecular level, those particles are constantly moving. So definition of vapor pressure, the pressure that's exerted by a vapor that is in equilibrium with its solid or liquid state. We talk about it in liquid because that's most often students can see it, it's easier to understand it, but this can happen in a solid phase as well. Remember, we've talked about substances that can sublime. Sublimation is going straight from a solid phase to a gas phase. The stronger your IMFs, the lower that vapor pressure. Because if you have stronger IMFs, it's harder for those particles to escape their solution or their system, the substance they're within. It's harder to escape. So the higher those IMFs holding them in solution, the harder it is to escape, the lower the vapor pressure. For a given liquid, that vapor pressure increases as we increase the temperature. If I increase temperature, these particles have more energy, therefore it's easier to escape. And again, volatile means easily vaporized, meaning it easily escapes into the vapor phase. And something that is volatile has a vapor pressure. So what is Raoult's law? Raoult's law has a general form, P sub A equals F sub A times P naught sub A, where P sub A is the vapor pressure of A over a solution, X sub A is the mole fraction of A in a solution, and P naught sub A is the vapor pressure of pure A. Vapor pressure of the solution is due only to the volatile component in the mixture. So if you've got a mixture and only one part of it is volatile, only that volatile substance will actually add to the vapor pressure because, again, it's the pressure of this piece that has escaped solution is now pushing down. So if I look at this, X sub A, my mole fraction, and again, remember, vapor pressure is only due to the volatile component. Theoretically, as I increase the mole fraction of that volatile substance, I should increase the vapor pressure as well. If there's more of that volatile substance in the solution, in the mixture itself, more should be able to escape, and therefore the vapor pressure should be higher. We do have two different cases we're going to look at. We're going to look at if we have a non-volatile solute and the solvent is volatile, and then we're going to look at if both the solute and solvent are volatile. First, let's talk about non-volatile solute and a volatile solvent. If A is your solvent and if only A is volatile. So if I've got some system where my solvent is volatile but my solute is not volatile, they will lower the overall vapor pressure of the system. So we see here, calm down and stop trying to evaporate. This is your non-volatile solutes. This is your solvent that is volatile. They lower your vapor pressure. They keep you in solution longer. Demonstration. Let's say we have pure solvent versus a solution. If I fill this graduated cylinder, and let's say I actually have pure solvent in here. I don't know why I never colored this in. I have pure solvent in here, and on the other side, I have a mixture of that solvent with something else. So for simplicity, let's say I have water. And over here, I have water plus sugar. Over time, if these are open containers, that water is going to evaporate away. Eventually, the cylinder that had water will be empty. No trace of the water left behind. It's just an empty cylinder. It just dried out, right? You can wash dishes, put them on the countertop, and not dry them by a towel, just let them air dry, and the water will eventually evaporate away. It may leave water droplets or something, but that's not the water itself. That's just other components that were in the water, like salt and stuff that can get stuck on the cup, unfortunately. But water itself will evaporate away. What about water and sugar? What I want you to think about is if you ever gone to a fast food restaurant, go through the drive-thru, and they give you a glass with your drink. If they do not wipe off the outside of that glass, and you then put it in the cup holder in your car, you don't think anything about it. Over time, though, you notice that the cup holder itself is sticky. Why is it sticky? Well, it's the sugar water, right? But sugar by itself isn't wet. Why is it sticky? What happens is this. This has sugar in it plus some water. Sugar is not volatile. It's not going to escape solution, but it's going to keep some of that water behind with it. It lowers the vapor pressure of the system. Not all of the water can escape, and therefore it makes it feel sticky, because now you've got sugar with some water in it, but not very much, leaving behind a sticky residue. In order to calculate this, we figure out, again, the actual vapor pressure of the system by taking the mole fraction of the volatile component and multiplying it by its pure or normal vapor pressure. How much would it be if it was not combined with a non-volatile solute? This is the same as saying P of the solution, pressure of the solution, is equal to X sub A times P naught sub A. Let's work an example though so we can see how this actually works. What is the vapor pressure of an aqueous solution? Remember, aqueous means water. That's formed by dissolving 20 grams of glucose, C6H12O6, which is a non-volatile electrolyte. That is a key. That is telling me I know water's got a vapor pressure. That's something you just have to know. Water escapes. Takes time. It does have strong hydrogen bonding, but it will escape into the vapor phase. But it's telling me my solute, so this is my solvent, this is my solute, it's telling me my solute is non-volatile. And it's in 100 grams of water at 25 degrees C. It then tells me, given the vapor pressure of pure water is 23.756 torr at 25 degrees C. This is the other hint this question is giving me. The fact that it's giving me the vapor pressure of pure water tells me that water is volatile. So even if I didn't remember that, it's giving me a hint to remember, hey, this is actually volatile. I need to pay attention here. So I know water is volatile. I know glucose is not volatile. I also know glucose is that should say non-electrolyte. I apologize. I have to fix that slide. I never noticed that. That should say non-electrolyte, which is important. We'll talk about how electrolytes behave differently in another module, but that should absolutely say non-electrolyte. I'll try to get that slide fixed. We know that P sub A is equal to X sub A times P naught sub A. And we know that we're looking at water, so we can actually say P of water, the pressure of the water, the vapor pressure of water, is equal to the mole fraction of water times the vapor pressure of pure water. So I want to know, what is the vapor pressure of this solution? So the pressure of the water of this solution, that will be equal to the mole fraction of water times the vapor pressure of water. I already have this. That's given right here. So can I find the mole fraction of water? Mole fraction of water is the number of moles of water I have divided by the total number of moles of my system. You can do this in partial steps. You can do this in one fell swoop. I don't care how you do it. Let's just write it out so everyone can see the whole process. Remember, number of moles of water. It tells me that I have 100 grams of water. Convert that to moles of water. (18.02 grams of water). This gives me 5.540 moles of water. So 5.540 moles of water. And to find the mole fraction, I have to divide it by the total number of moles of the system. So I know 5.540 moles of water, but I also need the number of moles of glucose I have, because that adds to the total number of moles of the system. Tells me I have 20 grams of glucose. And if I add up the molar mass of glucose, I find it to be 180.2 grams. 0.110 moles glucose. Overall, that shows me the mole fraction, 0.9805. That is the moles of water to the moles total. Now I've got all the pieces I need. So the pressure of my water is equal to 0.9805 times the vapor pressure of pure water, which is 23.756 torr. Overall, I get an answer of 23.29 torr. And that is the vapor pressure of the system. I do want to talk about just a couple things here really quick. First, sig figs. Note, I do have 3 sig figs here, but when I add these two numbers together, that gives me overall 4 sig figs. Because I'm doing addition, I need to keep track of the number of decimal places, which is why I keep 4 sig figs here, 4 here, 5 here. My overall answer has 4 sig figs. The other thing is, does this make sense to you? Does the answer make sense? Your vapor pressure has been lowered. The vapor pressure of pure water is 23.756. The vapor pressure of this system is 23.29. So yes, it makes sense because my vapor pressure has been lowered. Non-volatile solutes lower my vapor pressure. It has not been lowered very much though. But if I look at the mole fraction of this system, the bulk of this system is water. 0.9805 is the mole fraction, which means 98% of this solution is water. A very small amount of it is actually glucose. Only 2% is glucose. So yes, it makes sense that it hasn't lowered it a lot because there's not a lot of glucose there, but it has lowered it. That's what we mean when we say, does your answer make sense to you? I really want you to think about this process and think, does this answer make sense? What if you have a solution with 2 volatile components? What if both your solute and your solvent are volatile? That means that they each exert their own vapor pressure. By Raoult's law, we know that the vapor pressure of component A is equal to the mole fraction of A times the partial pressure of A. We know that the pressure due to B is equal to the mole fraction of B times the partial pressure of pure B. So we can actually say, by Dalton's law of partial pressures, the total pressure of the system is equal to the individual pressures. What is the pressure due to just A? What is the pressure due to just B? The sum of those is the overall pressure of the system. So P total vapor pressure of your solution. P sub A is the vapor pressure from A in your solution, and P sub B is the vapor pressure of B over the solution. We do have a couple different cases we can look at here. So first, ideally, a case of, with 2 volatile components, meaning solute and solvent. Theoretically speaking, let's say our vapor pressure of A, we've got your mole fraction here, and your pressure of A, your vapor pressure. As we increase the mole fraction, the pressure increases. We start at 0, we end at, we're showing here at 75%. Eventually we go up to 1. So if I have no A present here, I don't have any component A present, I expect it to not contribute at all to the pressure of the system. Makes logical sense. By the time I get to up to 75, I expect 75% of it, of the pressure of the system, to be due to A. B, I start with only B and end with no B. At the very beginning, when I only have B present, the vapor pressure is only due to the pressure from B. At the very end, it's only due to the pressure due to A. Theoretically, the pressure of the system should be the sum of these two. So that's been overlaid here. This is A, this is B. So the pressure total is going to be the pressure due to A plus the pressure due to B, the vapor pressure of A plus B. Now, that doesn't mean that it's always going to happen. That is an ideal solution. I apologize, I forgot this was written on this slide. An ideal solution is a solution that obeys Raoult's law, where the pressure is the sum of the individual pressures. That's behaving in an ideal fashion. But we know it's chemistry, and we know that things don't always happen in an ideal way. We can observe deviations from Raoult's law, and you are responsible for these deviations, and I need you to understand why and be able to explain it yourself. So we can see a positive deviation, positive meaning that the vapor pressure of the solution is higher than predicted. Positive deviation results when the solute-solvent attractions are actually weaker than solvent-solvent or solute-solute. Basically, we have a higher vapor pressure than we expect. What that means is it's easier for those particles to escape solution and go into the vapor phase. If it's easier for them to escape, it's because they're being held weaker. Their attractive forces between the solute and solvent are weaker. Therefore, it's more likely for them to escape into the vapor phase. When they're in the vapor phase, we assume they are no longer interacting with one another. They're just doing their own thing. So if those forces are weaker, then we will see a positive slope. Your vapor pressure is higher than predicted. You've got weaker IMFs. With that in mind, the negative deviation should make sense as well. A negative deviation from Raoult's law results when the solute-solvent attractions are stronger than the solute-solute and solvent-solvent attractions. The vapor pressure of the solution is less than predicted because you have stronger IMFs. VP for vapor pressure. The negative deviation suggests the solute-solvent attractions are stronger, and so it's harder for those components to escape solution. They stay in solution stronger. We see a weaker vapor pressure than we expect. Let's work an example, though, or a couple examples on how do I actually calculate this. So first, what is the vapor pressure of a solution that's formed by mixing 6 moles of methanol with 8 moles of propanol at 40 degrees C? At 40 degrees C, the vapor pressures of pure methanol and pure propanol are 303 and 44.6 torr respectively. Assume that this behaves in an ideal solution. Now, the hints this question is giving me. This question is telling me pure methanol has a vapor pressure of 303 torr and pure propanol has a vapor pressure of 44 torr. That is telling me that both my solute and solvent are volatile. So I know my total pressure of my solution will be equal to the mole fraction of methanol, MEOH is a shorthand for methanol, times the pure vapor pressure of methanol, plus the mole fraction of propanol times the vapor pressure of propanol. So I just need to find all those pieces. Well, I already have this piece, and I already have this piece, so I just need to figure out their mole fractions. Mole fraction of methanol you've got 6 moles of methanol divided by 6 moles of methanol plus 8 moles of propanol. And I didn't actually calculate this out, so I'm not going to calculate it out here either, but you can find the answer here. You can do the same thing for propanol. 8 moles of propanol, 6 moles of methanol, I should say mole in there, and then plug them into your system, or into your total equation. The pressure of this solution is equal to 6 moles of methanol divided by 14 moles total times the vapor pressure of methanol, which is 303 torr, plus the mole fraction of propanol, 8 moles of propanol divided by 14 moles total, times the vapor pressure of propanol, 44.6 torr. Gives me 155 torr. So the vapor pressure of this system is 155 torr. It's a combination of the two systems. We're assuming it's behaving ideally. We're assuming that there's no the intermolecular forces between solute and solvent are nor stronger nor weaker than solute, and solvent. It's behaving ideally, and the vapor pressure of the system should be 155 torr. Let's work a slightly more difficult example. A certain methanol-propanol mixture, so we got methanol-propanol again, but has a vapor pressure of 205 torr at 40 degrees C. Describe the composition of the solution in terms of the mole fraction of each component. At 40 degrees C, the vapor pressures of pure methanol and pure propanol are 303 and 446 torr respectively, and assume this behaves in an ideal solution. So now I need to work backwards. I need to find out the mole fractions. I have the total pressure. I have their individual vapor pressures. I know that pressure of my solution is equal to the mole fraction of methanol times the vapor pressure of methanol at 40 degrees C plus the mole fraction of propanol times the vapor pressure of propanol at 40 degrees C. I have this, and this. I have one equation and two unknowns. So what can I do to solve this question? The important thing to realize is that this system only has two components. I know that I only have methanol and propanol, and the mole fraction of methanol plus the mole fraction of propanol has to equal 1, because I only have two things. That means I can also substitute one in. So I can say you can solve for either one, but I'm going to say the mole fraction of propanol is equal to 1 minus the mole fraction of methanol. Again, you could do that the other way and solve for the mole fraction of methanol as well. It doesn't matter. But I can now take this piece and substitute it into my equation. Wrong direction. Substitute it into my equation for the mole fraction of propanol and solve the question. So I've got P of solution equals mole fraction of methanol times partial pressure, or vapor pressure of methanol, plus mole fraction of propanol times vapor pressure of propanol, both at 40 degrees C. Let's plug in what we know so far. We know the pressure of the solution is 205 torr. This is equal to the mole fraction of methanol times the vapor pressure of methanol, which is 303 torr at 40 degrees C, plus the mole fraction of propanol times the vapor pressure of propanol, which is 44.6 torr at 44 degrees C. Now I'm going to go ahead and substitute that in. So I'm going to have 205 torr equal to the mole fraction of methanol times 303 torr plus 1 minus the mole fraction of methanol times 44.6 torr. From here, it's just algebra. So let's simplify this out. 205 torr is equal to 303 torr x for methanol, mole fraction of methanol, plus 44.6 torr I'm distributing this through at this point. Minus 44.6 torr times the mole fraction of methanol. Get your numbers on one side, your variables on the other. So I'm going to say 205 torr minus 44.6 torr equals 303x minus 44.6x. And I'm going to move up here. 205 minus 44.6 gives me 160.4. 303x minus 44.6x gives me 258x. I dropped the decimal there because of the sig figs. Solve for the mole fraction of methanol here. My torr cancels out in the division here. Solve for the mole fraction of methanol, and I get 0.621. And I know that the mole fraction of methanol plus the mole fraction of propanol has to equal 1. So I can take 1 minus the mole fraction of methanol. I get the mole fraction of propanol, and it equals 0.379. So in this system, this methanol-propanol mixture at 40 degrees C, if the total pressure was 205 torr, that means about 62% of the system was due to methanol and about 38% of it was due to propanol. What about this system? I have two solutions, 10 grams of glucose in water and 10 grams of sucrose in water. Which of the following is true? Does the glucose solution have a higher vapor pressure? Does the sucrose solution have a higher vapor pressure? Do both solutions have the same vapor pressure, or is there not enough information to be able to compare the vapor pressures? I need you to think about these systems. I have 10 grams of each one. Okay. 10 grams of each one. Okay, cool. They're both in 1 liter of water. Cool. So we're very comparative at this point. But these have different molar masses. Glucose and sucrose have different molar masses here. These have a different number of moles, which means that they have a different mole fraction, which means they're going to have a different vapor pressure. So this one has a lower molar mass. If I have 10 grams of it with a lower molar mass, that means this one will have more moles if I have 10 grams of it. This has a higher molar mass. If I have 10 grams of it, I have less moles. It just takes more of it to get the same number of moles. So, how does that help me though? Well, what causes a higher vapor pressure? It's easier to escape. How do we calculate vapor pressure? P of solution is equal to the mole fraction times the vapor pressure of that solution. So if I know that I have less moles of something, think about your mole fraction here. We're specifically looking at water being able to escape, by the way, because both of these are non-volatile. These are both going to stay in solution. So we're looking at water escaping. I've got 1 liter of water in each, so my number of moles of water is constant. But the number of moles of total moles of my system is not constant. This is constant. This is constant. I want to know which one's going to have a higher vapor pressure. They're not going to be the same. I know they are not the same, and I do believe there's enough information. Which one's going to be higher? Well, this is constant, so what's going to change this? Number of moles. Number of moles of C6H12O6 or C12H2211. Okay, if this number is bigger, what does that do to this? The bigger that number is, the smaller my mole fraction becomes, right? What if this number is smaller? The bigger this becomes. What causes this to increase? A bigger value here. How do I get a bigger value there? A smaller value here. So a lot of algebra going into this thought process, but this is how my brain works it out. How do I get a smaller number of moles here? Something with a higher mass. The sucrose will have the higher vapor pressure. Sucrose has a higher molar mass. If I have the same number of grams of each species, then that means that I will have less moles of sucrose. Those less moles of sucrose will lead to a larger mole fraction, which will lead to a larger vapor pressure because more of that water will be able to escape solution.